Welcome to Apply Machine Learning for data exfiltration and other fun topics. You're in Southeast CDF and with your speakers today, Matt Wolff, Brian Wallace, and Xuan Zhao. And before we begin, a few brief notes. Stop by the business hall located in Bayside AB during the day, and for the welcome reception is going to be between 5:30 p.m. and 7 p.m. tonight. The Black Hat Arsenal is going to be at the Palm Fire on level 3, and you can join us for the Pawnee Awards in Mandalay Bay, BCD at 6:30 p.m. today as well. So thank you for putting your phone in vibrate or silence. It makes it easier for everyone to ignore the ringtones. And well, that's everything we've got. So please give a warm welcome to our speakers today. Thank you very much.
Thanks everybody for coming. My name is Matt Wolff, and Brian Wallace and Xuan with us today. Today's topic, applied machine learning for data exfil and other fun topics. So I've been talking about machine learning and security for several years now, and one problem I've seen is people come up to me and say, hey, I want to use machine learning in my organization. How do I get started? What problems make sense for machine learning? And so this talk is geared towards that. So this is if you hear about machine learning, you say, hey, I want to apply this, how do I do that? And so we're going to try and walk through here what you would look for, what problems make sense for machine learning, and start doing that. And as part of that, we go through several different tools that we're building, that we've built and released as part of this to give you sort of source code to go off of and go back to your labs or wherever and try to apply this to your own problems. So as I said, the goals are, one, what problems are going to make sense to take this approach for, how you do that, and my thought is I want to help jumpstart people researching this area if you're not already, because there are a lot of valid approaches where machine learning works great, and security is a great industry to apply that because we have an amazing amount of data that comes through every day. Obligatory silence slide, who we are. Cylance is an endpoint security company. We're built around AI. We're on a bunch of endpoints right now. And if you like looking at ridiculously awesome booths, stop by our booth 1124. It feels like you're on a Star Trek teleporter pad. So I recommend going to see that. Okay. As I mentioned earlier, we're going to go over several tools here that we'll look at a tool for Nmap clustering, a botnet identification tool, and then we'll show you how you can exfiltrate some data by sort of encoding it to look like normal text or normal traffic. Just to give you a brief overview of machine learning, how it works for those of you who aren't familiar with it. Machine learning is data-driven techniques. So typically you have a bunch of data and you want to learn from that data. And so that's where machine learning is useful. There's sort of two main classes of machine learning. There's unsupervised learning and supervised learning. Supervised means you have some labeled annotated data. So you know what the data represents, and that representation, it helps you solve the problem. As I mentioned, clustering is an unsupervised technique. So if you have a bunch of data and you want to find, you want to do some data mining. So you want to say, what are already interesting things in this data? You would use clustering for that. And so the Nmap example we give here will go over how to use clustering and how you can use that in your own problems. And then with classification, you can use that to give you answers to problems. So if you want an algorithm that tells you what something is, you would use classification for that. So what happens is, okay, I have some data. I want to do machine learning. How do I make that happen? And so what has to happen is, given your data, typically you have to transform that into some type of mathematical representation. That is usually called a phase called feature extraction, where as a domain expert you would say, what are things in this data that I think are important to make a decision? And what you would do is write something to pull those features out, and then you'd have a process of turning them to vectors. I call it vectorization. There's probably the term for that as well. But that basically means you extract some features from whatever data you have, and you turn that into some numerical representation that you'll use. And we'll go over this as some examples of how you do that, and you can reference our source code as well that's being released that shows you how you can turn your raw data into a format that you can start using for machine learning. Some recommended resources in this talk will leverage Scikit-Learn. Scikit-Learn is an open source machine learning platform in Python. It's a great toolkit to get started. If you want to learn about machine learning, you want to see what techniques are there. They have a relatively wide array of algorithms and approaches you can apply there. So if you're interested, I recommend downloading this and playing around with it. As I mentioned before, all the tools here are available on our GitHub, at github.com/spear. So you'll be able to look at the source code there, and if it's a great way to jumpstart some research for yourself. So if you have a problem, you can look at what we have, modify source code for your needs, and start applying machine learning today. Okay, and with that being said, I'll introduce Brian Wallace to talk about the Nmap clustering tool.
How's it going? Okay, I can hear. All right. So the first tool we're going to talk about today is Nmap clustering, and I imagine the majority of the room is aware of what Nmap is, but if not, Nmap is a port scanning tool which will tell you which ports are open on an IP address or domain that you're scanning. And Nmap can produce a large amount of data per IP address that it's inspecting. And it gets even more untenable if you're scanning a large number of IP addresses, like a /16 or something. So you can end up with a large amount of data coming out of Nmap, and maybe not the time, energy, or even concentration to kind of comprehend it all. So the idea of the Nmap clustering tool is to take all this data and use it as a means to determine whether an IP address is similar to another one, and extend that to then create clusters or groups of these IP addresses. In order to do this process, we need to do what's called feature extraction and vectorization, as Matt mentioned. Essentially what features are, they're pieces of information that we pull out in order to feed into the machine learning model. So this is information like how large something is, or how many ports are open, or if TCP/80 is open. Just kind of information that's either binary or a floating point number. Feature extraction is pivotal for machine learning, for the whole pipeline. It's also one of the more difficult parts for more advanced applications. In this case here, our features are based purely on Nmap output. So for instance, one feature would be TCP/80 is running Apache. That would be its own feature. And features are expanding further out. So TCP/80 is running HTTP, TCP/80, HTTP, Apache. So each port is a feature. We also include script output. So let's say the website title gets dumped out in a script, that ends up being a feature as well. And now for Xuan.
So when we have extracted these features, as Matt mentioned, we are doing this vectorization process. So for each feature, they are either a continuous feature, so we have a numerical value for it, or a binary feature, so we have a 0 or 1 for it. So we get all the numerical values for these features, and we stack all these values together into an array of values. So that array of values will be what we call as vectors. When we have these vectors, so these vectors are the numerical representation of our sample or our data. And when we have all this representation, we can fit it into all kinds of machine learning algorithms, not only for clustering. It can only be used for all the other machine learning algorithms and do all kinds of fun things. And vectors, we can view it as a point in a high-dimensional space. Will be very intuitive and easy to visualize if we are living in a two-dimensional space or three-dimensional space. For example, if we want to find the numerical representation for an executable, we can only use two features. For like the feature can be like a file name length, the file size. Here we give an example of notepad.exe. It has a file name length of 11 and have a file size of around 200. Then that point, the notepad.exe can be represented by a point can be represented by this point on this two-dimensional space with a y-axis at 11 and x-axis at 200. And the same thing for calc.exe. We can expand this feature space and add another feature to this representation. And we can add another feature kind of like size of headers. And then these executables can be represented as points in the three-dimensional space as we show in this picture here. So these are the vectors. And the vector, all this representation of vectors or the identification of vectors can be extended to many dimensions, higher dimensions like 4D, 5D, or ND. But as long as for doing visualization purpose, we can only visualize 3D. Another concept I want to introduce here is distance. So distance basically describes the discrepancy between 2 points, like whether two samples are too close to each other or the samples are far away from each other. The most intuitive way of measuring distance is the physical distance, like what is my distance to you guys. So that's the physical distance. If we want to measure the physical distance, we can use Pythagorean's theorem for doing that. This shows how we evaluate the distance between 2 points in 2D. And the same thing for if we are living in a 3D space. It's also the length of the straight line between that 2 points. But however, physical distance is not the only way we can measure distance here. It's a little bit counterintuitive, but actually all the measurement or all the operations that satisfy certain mathematical criteria can act as a distance measurement. For example, we can use Euclidean distance, Manhattan distance, LP norm, or cosine distance, anything that satisfies that criteria. On this picture here, all the lengths of these lines can serve as the purpose of distance between 2 points. Different distance measurement will be good for different problems or different situations. And if we have chosen a distance measurement, we can know whether 2 points are close to each other or 2 points are far away from each other. Based on this understanding, we can group the points which are close to each other under this distance measurement. And we can separate the points which are far away from each other. Like the points which are grouped together will be one cluster. So this whole process of getting this cluster is called clustering. Clustering is an unsupervised learning problem, as Matt just mentioned. And for unsupervised learning problem, we don't need the label information. Like we don't need to know what this sample is. We don't need to know like whether it's a malicious or whether it's a Botnet panel or something. We just need to know like the data itself. We just need to focus on the data itself. There are a lot of algorithms for doing this clustering, for doing like this grouping samples together thing. There are like DB scanning, like hierarchical clustering, k-means. But among them, the most popular should be k-means. So here I want to take this time to briefly introduce you guys to this algorithm. So for doing k-means, we first need to know how many clusters we want to cluster our sample to, like the number k. And then as an initialization, we can randomly assign the samples to these k clusters. Then we can calculate the center of each cluster, and we will assign the samples to the cluster where the center is closest to it. And then we can reevaluate the center of each cluster and redo the assignment. We do all these iterations until no samples will change its clustering assignment. Then we call it done, and we have our clustering. And here is an example of k-means. So for here, we choose k to be 3, like we want to result in 3 clusters. And all these black cross will be the center of these clusters. So with that said, we want to go through some demos with, using clustering.
Okay, so we're going to go through some demos with the Nmap clustering tool. So I'm just going to switch over to that. The first, actually I'll switch back real quick. The first demo we're going to do is the manual method. So this is, you define the clustering method you want and the hyperparameters or the extra little parameters that go into your clustering algorithm to determine how they work. After that, it's going to be the automatic method, which automatically picks the best clustering algorithm and the best hyperparameters for the algorithm itself. And here's just the help output of the tool. So what we're going to do is go through and say, we're going to use the strategy manual. We're going to use clustering method k-means. And we're going to use the k, or n here, for the number of clusters to be 3. And we're going to go into one of our sample data sets here on a VM network that was set up. So I've already done the Nmap scanning, and I've exported as the XML data for a small set of VM IP addresses. So now it's going to generate this output. And generally what it shows here is your different set of clusters and then which features that are shared between them in a string representative form. So in our first cluster here, we have 3 samples in it. And they all appear to be Linux running OpenSSH and Apache, which makes sense. Our second cluster here is 4 IPs all running Windows, very similar version of Windows. And our third cluster here is a separate cluster of Linux boxes running Dropbear and Nginx. Now for the automatic method, we're going to do something very similar aside for setting a lot of the hyperparameters. So we're going to say S automatic. And it's going to automatically pick our K as well as the clustering algorithm, our clustering algorithm and then the K. And in this case, it actually only produced 2 clusters. Now all of our Linux samples are in one cluster together, and all of our Windows samples are in another cluster together. And because of the decision being made here by the machine learning algorithm or the algorithm we have on top of it to pick their hyperparameters, there's not enough intuition being impressed upon this method to say what an individual might want to put clusters in. What the algorithm might want might be different than what is meaningful to a person. And that's why we've created this next method coming up called interactive clustering. Would you like to?
So as Brian mentioned, we want all the users to have their preference incorporated into this clustering result. Like different people will have different sense of who needs to be together with who. Like we want to, for example, cluster the bird, chicken, and monkey. Some people will feel like chicken and bird should be in one cluster, but some people will have a different opinion and feel like chicken and bird are different enough to be in 2 clusters. So this method, this interactive clustering method, just to give the users the opportunity to incorporate their own preference into the clustering, and then the clustering result will be customized. So how we did this? We start with all the samples in one cluster, and then we will ask the user whether these samples should be in one cluster or not. The users will have access to all the information about these samples. We will have a demo about this later, so you can get a sense of how it works. Then the user, based on all this information they get, they can decide whether these samples should be in one cluster or not. If not, they will click on split. Then the cluster will split into 2. And we recursively do this until the users are satisfied with all the clustering settings, with all the samples clustering assignment. So with this set, we will do a demo on this. And Brian again.
Okay, jumping over to the demo. So we're going to run the same tool. Essentially what it's going to do is it's going to pop up a mini web server locally where it's going to supply a web interface where you can do the interactive clustering. There is a command line version of it as well, but the visual version is much nicer. And we're going to use a different data set for this. We're actually going to use a chunk of Iranian network space. So it just tells you where to go to, so we're just going to open that in Firefox real quick. So what we've got here is a down projected version of our sample space. So all of our samples are in a high dimensional space, and we're projecting it down to 2 dimensions here. So this view might not be entirely representative of the actual distances in high dimensional space, but they're roughly similar. So what we're going to do is we're going to start by just saying start. And what this does, as Xuan mentioned, we're doing one giant cluster first. So we need to make a decision now, do we split or keep this cluster? And we're going to split. What we then end up with is 2 clusters, one over here and one over here, that are very large groups. And this group here, we do actually want to split again. So we're going to split that, split that, split that. So we basically keep splitting until we reach a point where we're seeing relevant clusters are existing. So in this case, we have looks like Windows 98 boxes on the internet for some unknown reason. So let's keep that cluster because that's what makes them interesting, right? And here we've got RDP server, so let's keep those. More Windows 98 boxes. We'll split that. Here we go, HTTP servers, more Windows boxes, more Windows boxes. And as we move to the right, we're actually going to start seeing more of Linux boxes. So we can split that, we can split that. Ultimately, this ends up being a much quicker process than guessing the hyperparameters and trying out a whole bunch of different things and analyzing the results because they're all right here. I mean, over here we have the overlapping features between them, but we can also hover over each individual item and kind of see all the features that are extracted for that individual IP. I'm just going to do some keeps here to shorten up the demo. And this big cluster over here is actually a bunch of microtick bandwidth test servers. So we actually have a large cluster of 73 IPs that are highly similar that would have been somewhat difficult otherwise to identify. And clustering is done. So now we're moving on to our next tool. The purpose of this tool is to identify command and control servers or botnet panels on HTTP sites. For anyone not familiar, botnet panels on HTTP servers very commonly end up looking like normal websites with login interfaces, MySQL servers, all this kind of normal LAMP stack that you see in a lot of applications out there. So it can be difficult sometimes to distinguish them between legitimate applications and then furthermore from each other. So the purpose of the tool is to identify whether we're in a web directory that has a botnet command and control server and then identify which one of that is based on the presets that we've trained on. In order to do this, we train a model in order to send as few requests as needed in order to accurately identify the command and control servers. Okay, so this is a classification problem. As Matt was saying earlier, we have supervised and unsupervised, so classification is a supervised problem. And what that means is that we have labels or we have some sort of annotation on our data that says this is what this is. So this requires a set of data to train on, and then we take the model that's produced by that training and we apply it other places. So we build the model, deploy it, and then we don't need to know what something is anymore because the classification model is just going to tell us. And classification really answers the question of, is it what we're looking for? Or is it A, is it B, based on what you trained it on? And classification methods can range from very simple to highly complex. In our example here, we're actually using a very simple one. So the features for ID panel are actually a bit different than most other projects I've worked on for machine learning. Essentially what we're looking for is a combination of HTTP response codes as well as comparing the content that's returned, because we want to be able to identify a result coming from a web request and combine it with the same response code for that same request. And encoding content can be, for these kind of features, can be difficult because you don't want to store the content for everything that you've seen and then doing the whole comparison. It's expensive time-wise. So what we're looking at using instead is SSDeep, which is a fuzzy hashing algorithm where you run your first content through SSDeep and it produces a hash. You run your other content through SSDeep and you get another hash. And based purely on these hashes, you can get kind of a fuzzy comparison between the two objects. So these hashes can be compared instead of the full contents of the files. So in order to build this model, in order to build this tool, we have to have our labeled data set. So we need to have a collection of not only known bot software, but also known bot panels that are existing in the wild, because we want to be able to get live data to accurately train the model. So for each one of these, or for each bot panel or each label, we identify every known resource that has been on bot panels like that, and then we put them into a big list together, and we make all those requests to every one of those bot panels. This is not stealthy, but the whole point is to not be stealthy for this portion, to be stealthy later on and minimize requests further forward. So the results are stored as a combination of HTTP status codes and SSD hashes. And we also collect data from sites that are not bot panels as well, so we can do the classification between bot panels and not bot panels.
So for doing this classification, like to tell what it is, we are using this algorithm called decision trees. Of course, we have a lot of other choices, but we chose the decision tree because of a lot of advantages. It's easy to train and etc. The process of training a decision tree is much like humans making a decision. For example, if a human needs to make a decision of whether a milk is spoiled or not, they will first see whether it has passed the use-by date, and then they will see whether it has it has passed the use-by date for 3 days or more days, and then they will see whether it smells funny or not. Based on all these criteria, which we call features, they can decide whether the milk is spoiled or not. And decision trees and machine learning is making the same process. The difference is humans are making the decisions based on all their previous knowledge learned from their previous experience, seeing all of these cases. But the machine learning algorithm, like a decision tree, will make a decision based on only the data it is fed in, like the training data. So if it only focuses on the training data, if we only train one decision tree, it has the possibility of over-focused on the data. So what it means is it will classify or identify all the data that it is trained in correctly. So it will get all the data it has seen correctly. But if you get any other data, it will get something wrong. So it will give you the wrong classification. So it means that the algorithm won't be generalized well enough. And this is against our will, because we want this model to be generalized to the other samples so that we can just tell what the sample is based on the algorithm. And this overfitting issue will be very significant when we want to classify the samples into multiple labels. In our case, we need to classify the samples into multiple different types of ID panels. Like for example, we want to classify into Pawnee or Dexter or Zeus or not a Botnet panel. So for doing that, we actually have 13 labels. For doing that, it will heavily overfit. So to resolve that problem, we actually can train multiple decision trees. Each decision tree will simply decide whether it is that label or not. So only two classes, that label or not that label. We can train multiple trees, and each binary tree doesn't have to use all the samples. It can use a random selection of samples, and it doesn't have to use all the features either. It can use the features that best serve the purpose of telling whether the sample is that label or not. So in that way, it has a lower possibility of overfitting, and also it limited the number of requests we make, because it doesn't need to use all the features. It can only request for that certain feature that it is using. So these are all the advantages. And here is an example of how we make the decision based on all these ensemble or like this bunch of multiple decision trees. So we will get all these decision trees to vote whether it is this label or not, and then we collect all the votes together. So if one label gets the most vote, we will say this sample belongs to this label. For example, here we have 3 trees training for pony, and 3 trees training for whether it's a Dexter or not, and 3 trees training for Zeus. And then we collect all the votes, and we can see that pony got 3 votes, Dexter got 0 vote, Zeus got 1 vote. Then we can decide that this sample is actually a pony. So this is like how we make the decisions based on the ensemble of decision trees. And now we want to demo how we apply this. Brian.
So not to anger the demo gods or anything, I'm not trying to connect out over a VPN on our wireless here to live botnet servers, but so for the purposes of the demo, I've mirrored them locally, just to let you know. So what we're going to do is we're going to open up, so ID panel ends up actually coming as a bunch of scripts, so I'll just do an ls here. The one we're going to be using is called classify panel, and this is just going to go out and reach out to the panel and try to classify what it is. So we're going to say Python classify panel, and the first argument that we put in is actually the model, which actually it's a JSON file, so it's pretty easy to read. And then I'm going to, actually, hold on, I'm going to do, here's the list of the local panels that I have for this. So we're going to go classify, bot panel, and then let's take one of these. And what it's going to do is it's going to go out and reach to the local HTTP server, making 39 total requests to the one server and identify what it is based on that. So we can see here that it's a pony server, and then which URL it's at, and then all of the total votes for each one of the labels. This tool is designed to be really easy to use, so you can actually just pass in, instead of the full URL, you can pass in a path to a list of panels to check or a list of web locations to check. And what it's going to do is it's going to reach out to them asynchronously, grab and classify as quickly as possible. So we can see here we've got Zeus, Diamond Fox, Pony, and BetaBot. But this is still a bit inconvenient, right? Like you have to open up a terminal, you have to connect out to it. So what we really want to do is throw it in Chrome, right? So we've written a Chrome extension that does this ID or the botnet panel classification. So what it does is every website that you go to, it's going to check these 39 requests and do identification based on that. And in order to get SS Deep into the browser, we had to actually convert it from C to JavaScript, which would have been a nightmare by hand. So we used a tool called mscriptin, which converts C to LLVM and then converts that to JavaScript, and it works beautifully. And this is available in the extension store now, I believe. So what we're going to do is actually just do a quick demo of that. I've got an offline version here. Okay. So we're going to grab one of the same panels as before and just drop it in real quick. And we get a notification almost immediately. I mean, doing 39 requests takes almost no time compared to doing thousands or, yeah. So this actually ends up being Zeus, and for anyone who can recognize Zeus, that looks pretty much exactly like a Zeus login panel. We can do another one as well that's going to be a bit more obvious. So this is a Diamond Fox panel, which, again, exact match for Diamond Fox, and then we can see here that it is Diamond Fox from the login panel. And then we can open it up to see previous results by just clicking on the icon for it and see, oh, hey, we've got a Zeus panel we've identified and a Diamond Fox panel here. Okay, so we're going to move on to our third tool, Markov obfuscate. And the idea of this is that outbound network firewalls tend to inspect the data that's being sent out of the network. And in really strict situations, they're going to be looking for exactly only what they want going out of the network to be there. So if they see anything they can't figure out or understand, they're just going to drop the packet. I mean, it's easy to encrypt data and show, oh, hey, this is not a credit card, this isn't proprietary information. But if they can't read what it is, they're going to drop it. So the idea is to use Markov chains to make something look like something entirely different.
So what a Markov chain does is to remember the pattern of a sequence. A sequence here can be a sequence of words, sequence of events, sequence of phenomena. So it will remember the pattern of how this sequence transit, like which event will be more likely to follow which event. And here is an example of 3 sequences, and we can tell from this sequence, from all these samples that B will be more likely to follow A, and A will be more likely to follow B, but A will be less likely to follow A, and B will be less likely to follow B. And based on this, we can generate sequences following the same pattern. Markov chain can be used in a lot of occasions. For example, it can do prediction. The example we provided here is the weather prediction. Like knowing the weather today, we can predict the weather tomorrow. And all this prediction is based on this transition pattern we learned from all the data or weather reports we have collected through all the previous years. And we can, so if today is sunny, like the probability that tomorrow is also sunny might be 99.9999% because we are in Nevada and California. It just doesn't rain at all. And if it's raining today, then it might still be 90% of possibility that tomorrow will be sunny. Another use case of Markov chain is doing recommendation. Like when we are watching videos on YouTube or Netflix, when we have watched some videos, they will recommend some other videos, similar videos to us. And here is an example. We have 3 movies here, which are kind of hacker related. The first 2 is hackers and war games. They are like very classical hacker movies, and a lot of hackers will like it. Another is Black Hat, which is a movie come out last year. It's not like our conference. It's like the Black Hat movie. So the people who like Black Hat might not be the people who like hackers or any hacker movies. They might be liking the movie where there are good-looking people inside. So perhaps the people who like Black Hat, we will recommend something like Twilight for them. But but like people who like hackers, we will say like they might also fall in love with war games and vice versa. So based on all these learnings, we can recommend the movies to them. And we will have cooler applications of Markov chain, which we are going to demo here. Brian.
So in order to encode data with a Markov chain, what we're going to be looking for is what we can refer to as like a nth most likely transition. So let's say we're given a state, or we're at a point. So we have a word that's already in our document that we're going to send over. And we already have a transition matrix, or the probability that each item is going to follow this one word next. So we want to then sort these values and then pick the nth, or let's say the 5th, if we want to encode 5. And we follow that word up then with that next word, the 5th most likely to follow. And if we train models on both sides of a communication channel with the same data, the other model on the other end can very easily identify that was the 5th most likely, and have identified the transition of the number of 5. So we're going to do a quick demo here. I think we're running short on time, but so essentially what we're going to do is we're going to take a book from Project Gutenberg, we're going to train on that, and then we're going to observe the transitions from word to word, and it's going to generate the data based on that. The data that we're going to encode is a private key, so just so you know what it looks like there. So we're going to say obfuscate -h just to get the arguments. Book. So the 98.txt is our book, and then we're going to pass in our private key. I'm going to just tee that out to, I don't know, oh yes. So it's training on it, and then it's going to output to standard out. So what we see now is something that looks nothing like a private key, right? Like it's English text. Now a person reading this might not believe that this was a human-generated text, but it'd be exceedingly difficult for an outbound firewall to be able to determine that this wasn't human-generated text. Oh, and what we do with that then is say, we pass in the -d flag with the same other arguments, as well as our obf.txt, and what that's going to do is train the model again and then output the data. So it's a very seamless transition from private key to human text back to private key. So we're going to have a bit of fun with that. So what we did was train a model based on Taylor Swift lyrics, and we're also taking another model, training that based off of MIDI data from Taylor Swift songs. So we're going to use that along with the festival text-to-speech engine in order to make Thailand Swift, if you will. Hopefully the audio works.
I will never let you, and we will be here you were trouble when we will be, so I will never did you, and we will be here right there, I, and you and your eyes, and we had to meet, and the way you, and I will never did you, I could have been, cause I will never let no one of us off, and we will be here right here, I, and you know you, I could have been, so here's to me, so here's to me, so here's to me, and your name, I have got a long where you were Christmases be here.
We're going to start wrapping up with Matt.
So first off, I hope we didn't offend any fans of Twilight with that previous comment. So like I mentioned, the goal is really to spur research in this space, and there's a lot of great opportunity in the convergence of machine learning and security. Black Hat does that, so you have 3 takeaway points as part of your slide. So what I'd like to say is here are 3 points. When you go back and look at problems you're facing, anything with lots of data, as you can see here, you can start putting that through these different algorithms and finding solutions for that. Even if you don't understand machine learning, maybe you don't understand calculus or linear algebra, that's fine. There's lots of great online resources that you can get started with today where you may not need that math background or intuition right away to start playing around with these techniques. And if you have data where you can label it, you can annotate it, the classification techniques we described are certainly helpful in helping you find data from there. So with that, that's the end of our talk. So thank you.